So most of you, I assume, is probably familiar with the time domain representation of signal. An oscilloscope display, is a very good example display of a time domain representation, because in an oscilloscope, in one scale or in one axis, a voltage or amplitude is shown, and in one scale also or in the other axis is the time. While signals also can be represented in frequency. A good example that can be shown in frequency domain is the spectrum analyzer. So in frequency or spectrum analyzer, amplitude or power is shown in one axis and frequency on the other. So instead of time, the x-axis is represented in frequency. Notice that our the way of representing the signal in frequency domain fails to show one thing. It fails to show the phase of the signal. The signal in figure 1.4 could be a cosine wave just as easily as sine wave. So we cannot determine if it is a sine wave or cosine wave if it is in frequency domain. Nevertheless, frequency domain representation are very useful in study of communication system. For instance, the bandwidth of a modulated signal generally has some fairly simple relationship to that of baseband signal. With that, this bandwidth can easily be found if the baseband signal can be represented in frequency domain. Any well-behaved periodic waveform can be represented as a series of sine wave or cosine waves at multiples of its fundamental frequency, plus sometimes a DC offset. This is known as Fourier series. Fourier's discovery applied to a time-varying signal can be expressed mathematically in this equation. So where f of t is any well-behaved function of time as described above, for our purpose, f of t will generally be either a voltage or a current. A sub n and b sub n are real number coefficients. That is, they can be generally positive, negative, or zero. And omega is the radiant frequency of the fundamental. So the radiant frequency can be from time domain representation of the signal. By finding a period using the equation, we can calculate the frequency. So frequency is equal to 1 over the period. And computation of omega is equal to 2 pi f. So we have an example here. Let's try to solve this problem. Find and sketch the Fourier series to the square wave in this figure. So let us look at this figure first. So we determine that it is a square wave. So let us first step. Okay, let me write it here. Solution. Let us first find the frequency. Frequency is equal to 1 over the period. So from that, let us determine what is the period. Period is the one cycle that it repeats itself. So as you can see, we have started at 0, then at rising edge, then it rises again in 1 millisecond. So the period is 1 millisecond. So frequency is equal to 1 over 1 millisecond. So therefore, frequency is 1 over 1 millisecond, meaning we have frequency of 1 kilohertz. Okay? So we have frequency of 1 kilohertz. So let us write it here. Frequency is 1 kilohertz. Now, let us solve for omega, or the radian frequency. The radian frequency is equal to 2, okay, where is that? Radian frequency is equal to 2 pi f, which is equal to 2 times pi times 1 kilohertz. Therefore, we have the radian frequency of 2 pi times 10 to the power of 3 radians. So that is our radian frequency. Okay, let me write it here. Let me write it again here. So we have omega is equal to 2 pi times 10 to the power of 3. So now our problem now is to find the Fourier series of this square wave waveform. So in this succeeding figure or table, we will be finding the Fourier series representation of different signal. So we have this Fourier series for common repetitive waveform. So we have half-wave rectified sine wave signal. So here is the Fourier series representation. Then we have full wave rectified sine wave, and with time 0 at voltage at 0, and with time 0 at voltage peak, we have the corresponding Fourier series representation. Also, we have the square wave function that we are finding, which is an odd function at rising edge at 0. So we have here, this is what we are looking for. V of t is equal to 4 times the amplitude over pi times the sine omega t plus 1/3 sine 3 omega t plus 1/5 sine 5 omega t plus so on and so forth with decreasing value. And we also have the even function and this corresponding sine wave, Fourier series rather. Also we have the pulse train, the triangular wave. So this Fourier series representation is uploaded in our LMS and Google Classroom so that you can refer it anytime and practice, and we can use it in our problem solution. So take note of this equation in solving our problem here. So from that corresponding table, we find that the Fourier representation of the square wave with odd function is equal to V of t equal to 4 times the amplitude over pi times sine omega t plus sine 3 omega t, oh I forgot the 1/3, 1/3 plus 1/5 sine 5 omega t plus so on and so forth with decreasing value. Oh, is it still clear with you, or shall I just write it in a blank blackboard? I think. Okay, let me pause it for a while. So I have here a blank blackboard. Okay, so let us try to recall. So to solve the Fourier series representation of the square wave earlier, let us recall frequency. Okay, why is my pen not working? So the frequency is equal to 1 kilohertz. Then we have also solved the radian frequency, which is equal to 2 pi times 10 to the power of 3. So from the table earlier, we have found that the Fourier series representation of the square wave is equal to v of t is equal to 4 times the amplitude over pi times sine omega t plus 1/3 sine 3 omega t plus 1/5 sine 5 omega t plus so on and so forth. So this is an infinite series with decreasing value. So let's try to substitute. So we all have our values already. So for what is our amplitude in the square wave? Try to recall. It is equal to 1 volt. So therefore 4 times 1, we have 4 over pi times sine omega. What is our omega? Omega is equal to 2 pi times 10 to the power of 3. So sine 2 pi times 10 to the power of 3 t plus 1/3 sine 3 times omega. So 3 times 2 pi, so we have 6 times 10 to the power of 3 t plus 1/5 sine 5 times 2 pi. So we have, we have forgotten the pi here. 6 pi. Okay, my mistake. Okay, sorry. So back again. So sine 5 times omega is equal 5 times 2, we have 10 pi times 10 to the power of 3t plus so on and so forth. So this is our Fourier series representation of the square wave. So this equation shows that the signal has frequency components at odd multiples of 1 kilohertz. This is at 1 kilohertz, right? And this is for the 3 kilohertz and for the 5 kilohertz. The 1 kilohertz component has a peak value of, at 1 kilohertz, we have a peak value of 4 over pi. So that is equal to 1.27. And for the other components, at third or the 3 times the fundamental frequency at 3 kilohertz, so we have the amplitude of 4 over pi times 1/3. So we have 4 over 3 pi or 0.424 volts. And the fifth component, we have 4 over pi times 1/5 is equal to 4 5 pi. Let me erase it. 4 over 5 pi, or it is equal to 0.255. Okay, so that is the sum of the components of the fundamental frequency at 3 kilohertz. At fundamental frequency rather. So if we are trying to plot it in frequency domain, so we have at V1 we have 1.27, V of 3 0.424, and V of 5 is 0.255. Then we have, this is our frequency. Okay, forgive my oh, this is so bad, my drawing is so bad. Okay, let me try to draw it beautifully. Okay, so we have the frequency of 1 kilohertz, 3 kilohertz, 3 kilohertz, and 5 kilohertz, and we have the amplitude here at 1. So what is the amplitude at 1 kilohertz? So this is frequency at kilohertz, okay, and this is the amplitude. So at 1 kilohertz we have 1.27. Okay, 1.27. And at 3 kilohertz we have 0.424. And at 5 kilohertz we have 0.255. So this is, okay, so this is the frequency representation or the frequency domain of the square wave function that we have presented earlier. Okay, so we have here some figures, before anything else. So the time domain and frequency domain are just equivalent. They're just different in a way that they are represented. So in time domain it is represented with respect with time, and frequency it is represented with respect to frequency. Actually it can be restored back and forth in such a way. For example, we have here in the figure, we try to restore the square wave waveform by adding the components of the Fourier series components. So we add it up. Actually, this simulation is added through computer simulation rather in manually. So in figure 1.6 here, we have the result of adding two components of the Fourier series. It resulted here in a time domain like this, a small distortion, and also we have here the addition of four components from four Fourier series, and then this is the result. And if we add 10 components of the Fourier series, this square wave is more slightly beautifully restored in its original value. So if we add it up in more, then the construction of square wave would restore closer to its original form. So just be careful when adding it up, because if we add the waveform in its wrong phases, then it could result like this. So instead of sine wave, if we have added in a wrong phase, then in a cosine wave, then our waveform would not restore to its original value. So it would just look like this. So just be careful and tend to be careful with the face angles. So I think that is the end of our topic for that session. So for the next session, we will discuss about the noise communications and spectrum analysis. Thank you for listening.